Okay, so final note, quick note on what the actual Google's PageRank algorithm is doing. And we saw that potentially a complaint to the previous idea was that if there's some page that just recently joined, it won't be in on the process, right? No way for this random web surfer to get to a page that just got added to the internet. And maybe you have kind of maybe the internet splits into two, right? And kind of half the pages are linked from the other half, and you have bigger problems, I guess, in that case. In any case, so the fix is going to be to add this little caveat that you still proceed to go from page I to page J, by clicking on these random links, but you do so only with probability 1 minus q for some parameter q, and you go to a random page, meaning just completely out of the blue, think of a brand new URL, and just tell what's called teleport to that random web page with probability q, right? So you essentially land on each page, and then you decide on whether you want to go somewhere else completely at random with probability q, or with probability 1 minus q. You do the same old thing, which is look through the links on that page, pick one at random, and move on. So what does this do? It changes the PageRank equation slightly. So the global balance relation is still the same, but the one-step transition probabilities now look like this, right? Where with 1 minus q probability, you follow the links, and you teleport kind of randomly with parameter q. If I recall correctly, and I could be way off on this, but I think Google actually uses something like 0.15 for q, but it could be wrong here. Once you take this transition probability, which notice what this accomplishes is that sort of it ties all the web pages together. Now, that previous example that I had on the board here, it wouldn't work in the same way, because now all of the web pages are tied with at least some probability, right? Maybe a small one, but there's always a probability of going to from any page to any other page. And then on top of that is superimpose this original web surfer process. And then once you plug everything in, this is the final page rank, right? You're kind of given a starting value, right? Every web page that comes in is given this tiny little rank, right? So now everybody kind of starts off positive, and then the rest is exactly the same as before. Your page is only as important as how many other important pages link to you, right? And so this is a sum from I, obviously from I from 1 to n. This is I equal 1 to n. So the sum is exactly before, but it's now weighted as 1 minus q. And then in matrix form, right? This is what usually you see is this equation appearing in matrix form. These are my global balance relations written in matrix form. Here pi is the row vector corresponding to the stationary distribution, and p is my matrix of one-step transition probabilities. And I've written it out in this form. So this E transpose, so E is going to be a vector of all ones. And if you've seen kind of matrix multiplication, if I take a column, and this is going to be, actually I should say that this is going to be a column vector, so I'll put a transpose here to make this into a column vector. So if you're not familiar with this, basically, let me just kind of give the basic intuition. When you take a column vector, right, a vector written like this, not the way I wrote horizontally, but row-wise, and you multiply by the transpose, which is written which is a row vector, right? If you multiply a column vector by a row vector, you get a matrix. And because every vector here is 1, this multiplication here represents an n by n matrix with every single entry equal to 1, right? And obviously that's why, it makes sense why it's true, because for every single page I, we got exactly the entry qn times 1. That's what this E times E transpose represents. So I'm writing I had to write a matrix form, so I can't put q just q over n. I have to multiply by an n by n matrix with all entries equal to 1. Here I put this is D inverse L. This is also related to your homework, but D will essentially sum the rows of L and multiply by L to get transition probabilities corresponding to the link matrix L. So this is also something that appears on your homework, so I won't say too much more here. But if you kind of get that exercise, you'll see exactly what I'm talking about. And then what's the final, two final pieces to mention. So first came kind of this, I don't remember if this was in the original paper or not, but if you kind of see how Google actually, well, who knows at this point what they really do, but at least originally how they were computing the stationary distribution, it's done through this iteration procedure where you start with some pi, pi k is going to be some current version of the stationary distribution or some current PageRank. If you multiply it by p, you get an updated PageRank. And you do this kind of procedure over and over and over and over, and eventually, and this is something you can try, maybe you've seen it in 160A, if you run this procedure for a finite state Markov chain, it will converge to a stationary distribution. But that's maybe not what really Google is after here. What you're after here is the fact that this matrix P is also changing, right? These links are changing all the time, and so this matrix is being updated. And so you want to kind of not have to solve this big system of linear equations, right? Google doesn't want to solve this system every single hour, right after some guy adds a website, and all of a sudden you have to solve a giant set of equations. You don't want to have to do that. And so you have this just one multiplication that gives an update that basically results in an approximate PageRank, and that if you do this frequently enough, it's just as good as the final solution. So you don't need an exact PageRank all the time. You just basically update your matrix P and then update your PageRank by just this multiplication. So essentially there's going to be this web crawler that's updating this P by updating the L, and once every, I don't know how often this is done, maybe hourly, maybe just once a day, you update the PageRank just by doing this row vector multiplication. Then there's one final thing to say. This E is sometimes replaced by a different vector. I could call it maybe vector V. I think that's maybe the convention that's followed, and that represents what's called personalized PageRank. So you can add a vector V there to make sure that the ranking for each person is quote unquote personalized, and that's how you can accomplish that. When you do a Google search from the United States, or you do it from Europe, you'll get different results based on sort of your location, and these results can also change based on your browsing history, so on and so forth. So those are kind of complicated issues, and I'll let you kind of explore them on your own. So that ends sort of our set of examples. In terms of reversibility, you can see here we're using global balance everywhere. You can try to think about when this is reversible, and again, it will have to come down to when every page that you link to links to you. Then you're in this reversible random walk context, right? Just as you have in your homework, where the PageRank equals how many links you're able to collect on your page, right? But it's not that easy to collect them anymore, as we mentioned in the previous video. When you want to link to someone, right, you have to convince them to link to you, and that will give you a reversible random web server process, which, by the way, would be much easier to update and solve, right? You wouldn't have to do this whole matrix vector multiplication. It would be in the reversible, if this chain was reversible, and if the internet had this rule that everyone who links to someone has to get a link back, then the PageRank would be much easier to compute, and there wouldn't be nearly as much research on this topic. Anyway, I think that wraps up lecture 6. So see you next.